This video discusses integrals that involve both exponential or logarithmic functions, or possibly both at once. This is for section 5.6 out of the OpenStax Calculus book, volume 1. You'll remember that an exponential function is basically Euler's number e raised to a variable power. It is its own derivative and its own integral. This makes them by far the easiest functions to work with. The integral of e to the x dx is e to the x plus the unknown constant that you get with the family of antiderivative functions. What if, however, the base of the exponential is not e, Euler's number, but instead some other constant like 5 or 2 or 10? What would be the integral of 10 to the x? Well, because it's an exponential, it's similar to e to the x, which means that you do get the integral of a to the x. But to compensate for the fact that the base is not Euler's number e, you must divide by the natural log of the base, which is a. Be sure that you do not try to use the power rule on e. Exponential functions have constants in the bases and the variable in the power. The power rule is used when the variable x is in the base and the power is a constant. You cannot use the power rule for exponential functions. Let's take a look at example 1. We'll use our formula to compute the indefinite integral of 2 to the x dx. Remember that indefinite integrals will give you the antiderivative function, but not the area under the curve. The area under the curve is reserved for definite integrals, which definitely have limits of integration, and this one does not. The integral of an exponential is the exponential itself, in our case, 2 to the x, but because the base of this exponential is 2, and not Euler's number e, I need to divide by the natural log of the base. The rule still applies in the case of the exponential with base e, but the natural log of e is of course 1, and that's why it doesn't show up when you look at the formula. Then we have to add on to this the constant c, which gives us the family of antiderivative functions. That's it. There's nothing more to do. Let's look at another example. This is the problem to compute the indefinite integral of 3 to the negative x power dx. There are two good ways to solve this problem. We'll show these two ways on either side of this long blue line. On the left side, what I'm going to do first is rewrite this, but without the negative power. I can do that by thinking of negative x instead as 3 to the negative 1 times x power. Because I've pulled the negative away from the x, I can then think of this as 3 to the negative 1 power to the x power dx. When the rule is 1 base, 2 powers, you multiply the powers. 3 to the negative 1 power, however, gives me 1/3. I can then think of this as the integral of 1/3 to the x power dx. Since my base is now 1/3, then I will need to compute the following. I will get for the integral the exponential function itself, still raised to the x power, but divided by the natural log of the base, which is 1/3. Now let's look at it slightly differently. Let's do this one again, but instead let's use a u substitution. In this case, I'm going to look at the problem 3 to the negative x dx, and I'm going to let u equal the negative x. Remember that we take the derivative of u with respect to x, which would give me -1. Then we abuse the notation by swinging the differential from the denominator type location to the other side. It's not really a denominator because it's not really a fraction. but this does let me write negative dx. In the equation, I do not have a negative dx, but I do have dx. So I'll solve this for dx by dividing both sides by the negative 1. This leads to the following representation for dx. Dx is equal to negative du. Now I do a u substitution. To substitute, what I want to do is replace the dx with negative du. In the integral, this will now let me replace 3 to the negative x with 3 to the u, and dx with negative du. The negative can be brought to the very front and even the outside of the integral since it's the constant negative 1. Then I have 3 to the u du. That I can integrate using the formula we've had previously. This would give me negative 3 to the u divided by the natural log of u. In order with a constant, don't forget the constant. In order to back substitute, I need to get out of u and back into x. To do that, I replace the u with what I originally set it equal to, which is negative x. This would give me negative 3 to the negative x divided by the natural log of the base. The base up here is still 3. The negative is not a part of the base because it's not in parentheses. Then I have the plus c. These do not look the same, but they are in fact the same thing. Let's see how they are in fact equivalent. In order to turn one into the other, I can take a look at this one and see if I can turn it into this one, or I could go vice versa. I think it will be easier to work with this one. First, remember that I can rewrite 1/3 as 3 to the negative 1. Let's do that now. That would give me, in parentheses, 3 to the negative 1 to the x. In the denominator, I have the natural log of the ratio of 1 to 3. A natural log of a ratio is the difference of the natural logs, which gives me the natural log of 1 minus the natural log of 3. However, the natural log of 1 we know is 0. That leads to negative the natural log of 3. This lets me rewrite this one as 3 to the negative x in the numerator with a negative natural log of 3 in the denominator. And don't forget, we should still have our plus c, which seems to have somehow disappeared. The c should be kept following along. Notice that if I lifted the negative to the numerator, I would get exactly the same thing as I have on the right side. These are two different ways of approaching the same problem. Let's take a look at another example. In example 3, I'm asked to compute the indefinite integral of e raised to the negative 3x power. In order to do that, I could think of this as e to the negative 3 raised to the x, or I could use u substitution. Typically, what we do is we do use u substitution. It is by far the most common way to approach this problem. That means that u will be the power negative 3x, and my derivative with respect to x would be negative 3. We abuse the notation by swinging the dx around to the other side to join the negative 3. This lets us solve for the differential du and write it as negative 3 dx. When I look at the integral, I do not have a negative 3 factor, but I do have dx. So I solve for dx by dividing both sides by negative 3. Now I can substitute du divided by negative 3 for dx, and u can replace the negative 3x in the power of the exponential. Let's write this part down. This gives me the integral of e to the u times, replacing dx with du over negative 3 gives me du, and I could pull the negative 1/3 straight out front if I want. The integral of e to the u is, of course, still e to the u plus some unknown constant. Then I back substitute for the value of u, which would give me negative 1/3 e to the negative 3x plus a constant. That's the end of that problem. There's no more work to be done there. Let's take a look at another example. Example 4 is another problem where we need to use u substitution. In this problem, it can be a little bit more difficult to figure out what to pick for u, but in general, when you have exponentials, the power on the exponential is often a good choice for u. Then look to see if you have its derivative as a factor in the integrand. That means that I'm going to choose u to be negative x cubed. Du then would be the derivative of negative x cubed, which would give me negative 3x squared. I can go ahead and abuse the notation and swing the dx around to the right all in one step. I will replace the negative x cubed with u. However, I do not have a full negative 3x squared. I do have the x squared and the dx, but I'm missing the negative 3. I'll move the negative 3 to the other side. You can write du over negative 3 equals x squared dx and just replace that part. Or you can think of it differently and go ahead and solve for just the differential dx by writing du over negative 3x squared. You can do either substitution factor, but you need to be careful to make sure that you don't mess up. I'll do the first substitution in red so you can see how it works, and then rework it using the substitution in purple. In this case, when I substitute using the red substitutions, the x squared becomes a part of the differential, and x squared dx, which is this part you see here now ringed in red, will get replaced with du over negative 3. This will give me e to the u du over a negative 1/3. That will give you the negative 1/3 out front. The integral of e to the u is, of course, e to the u. And the next step, I would replace the u back again with the negative x cubed. This gives me negative 1/3 e to the negative x cubed plus a constant. What would happen if I had done the purple substitution instead? In the purple, I would still be using the same u factor, which is up here at the top, now boxed in purple as well. That would give me the integral of e to the u, but I would replace only the dx with du over negative 3x squared. Because this has the variable x in it, I cannot pull it to the outside of the integral. Nothing with the variable x can pass the integral symbol. So instead, I have replaced only the e to the u, but not the x squared. I still have x squared in the problem, and now I replace just the dx this time, only that part, with du divided by negative 3x squared. When I do that, you'll see that I have a common factor of x squared in the numerator and denominator, so those parts cancel. That gives me my common negative 1/3 factor, which I can take out to the front. That leaves behind the integral of e to the u du, which is the same thing I got with the other substitution. And this, of course, will lead to negative 1/3 e to the u plus a constant, resulting in exactly the same formula that I got the first time. This leads to negative 1/3 e to the, what was it? Negative x cubed plus c. Let's take a look at another example. In example 5, we're asked to compute the indefinite integral for e to the sine x power times cosine x. It's very important that you keep straight what's in the base and what's in the power and what is not in the base or power but is a factor on the line. If I exaggerate this, I can rewrite it as e to the sine x power times cosine of x. When you have integrals like this, you may want to exaggerate the power position so that you don't mistake something in the power for being on the line or vice versa. To solve this problem, we again need u substitution. Again, we look to the power on the exponential for a good place to find our u. In this case, I believe that u should be the power, which is sine of x. Computing the derivative of that, I get cosine of x, and the abuse of notation slides the differential around to the other side so that I can solve for du. I do have cosine of x dx, so I replace cosine of x dx with du when I do the substitution. This leads to the following indefinite integral, e to the u du. The integral of e to the u du is, of course, e to the u plus the unknown constant from the family of antiderivatives. The next thing I need to do is back substitute out of u to get back to the original variable in the differential, which was dx. Back substitution leads me to replace u again with sine of x and gives me the answer e to the sine of x plus a constant. The next thing that we want to talk about in this video are integrals that involve logarithmic functions. Now, when we say they involve logarithmic functions, we're giving you the three different versions here. The one that we primarily work with, however, is the first one at the top, which I'm going to outline in red. The bottom two are not used as often. The bottom one is rarely used since we pretty much always stick with a base of e. The one in the middle, you will learn a better way to find this in Calculus 2. In this course, you'll simply have to use the formula since you have no better technique. Let me rewrite the bottom two formulas in a different form so we can copy and paste them when we need them. The integral that is boxed in red is by far the most important one you'll learn in this section. However, its format is not always the way it appears. Remember that x to the negative 1 can be written as 1 over x. This is a somewhat more common way of writing this indefinite integral. The integral of 1 over x dx is the natural log of the absolute value of x plus c. Why do we need the absolute values? Well, natural log is only defined on a domain of open 0 to positive infinity. That means that we cannot allow the base to be non-positive. We can't allow 0 and we can't allow negatives. 0 is already out of the running because the original integrand is 1 divided by x. The domain of this function does not include 0, so 0 is already tossed out. However, this function does not exclude negatives, so in order to force this to be realistic, given that we have a natural log function, we have to force the argument to natural log to be strictly positive by putting it in absolute values. I will require you to use these on your exams. Let's take a look at some examples. In example 6, we're asked to find the antiderivative function of the log base 3 of x. Keep in mind that this is really just asking you to locate the indefinite integral of the log base 3 of x with respect to x. This will give us an antiderivative family of functions up to the constant c. Looking at the formulas above, the one that we need is the one here where the base is a, where a is not necessarily going to be Euler's number e. In order to apply the formula, I will multiply x by the natural log of x and subtract x in the numerator. This gives me x natural log of x minus x. Because the base, however, was not Euler's number e, I need to divide by the natural log of the base. This is similar to what we saw earlier with the exponentials. This will give me the natural log of 3 in the denominator plus a constant. That's all I need to do to take care of that one. There's really nothing else involved in doing that. It's simply apply the formula and try not to mess it up and make mistakes with the negative signs. Let's take a look now at another example. In example 7, we're asked to compute the indefinite integral of 1 divided by 2 times x with respect to x. Keep in mind that the 2 in the denominator could be thought of as a common factor of 1/2. In other words, I could think of this as 1/2 times 1 over x dx. Then because the 1/2 is a constant, I could take it out of the integral, and that is probably what I would do. This would give me the integral of 1/2 times 1 over x dx. This is, in fact, one of the formulas we had above in the revised form that I wrote here in pink. This is the natural log of the absolute value of x plus a constant. In our case, because of the 1/2, we will have a 1/2 factor multiplied by the natural log of the absolute value of x plus a constant. Keep in mind that this 1/2, due to the rules for natural log, could be brought inside onto the absolute value of x. This would represent the 1/2 power, which of course would be the square root. To be honest, I probably wouldn't do that, but it is possible, and on occasion it will be necessary. Let's take a look now at example 8. This is a really tricky u substitution. It's not clear at first what's the best choice of u. You do have several good places to look for u. You have denominator, which is a good place for u. You also have something being raised to a power. The base of that is also a good place to find u. And you have a natural log, so the argument to natural log, which here is x, is also a good place for u. When trying to decide which is the best choice for u, look for something whose derivative or part of the derivative is already in the integrand. In that case, my attention is directed to natural log of x. I know that the derivative of natural log of x is 1 over x, and I can see a 1 over x already present in the integrand. That makes the best choice for u in this problem to be the natural log of x. Then du becomes 1 over x dx. The next thing I can do is I can substitute natural log of x out for u instead. And since I do have a 1 over x dx, I can replace that part of the integrand with du. Let's go ahead and make those substitutions now. This will lead to the following: the integral of 1 over u squared, since it was natural log being squared, and the rest of it, 1 over x and dx, become replaced by the substituted du. Now that I have it written in this format, I can remember that a denominator power function can be lifted to the numerator by changing the sign of the exponent. This gives me the integral of u to the negative 2 du, and then I can use the power rule for integrals to evaluate. This gives me u to the negative 1 divided by the new power negative 1 plus the constant representing the family of antiderivative functions. Now I need to get out of u, but before I do that, it's probably easiest to go ahead and rewrite it in a better form. The negative is a floater and can go anywhere, top of the fraction, denominator, or out front. U to the negative 1 becomes u to the first power in the denominator. And then, of course, I still have plus c. Now I want to substitute in place of u the natural log of x. This gives me -1 divided by the natural log of x plus a constant. That is my final answer. In this case, the natural log of x doesn't take the absolute values because they weren't there in the beginning, but in fact they are implied, since natural log would not be defined if x were 0 or negative. Now let's take a look at example 9. Example 9 is not one that involves exponentials or logarithms. It is simply a more complicated u substitution involving a trig function. In this case, I have different places to look for u. Good places for u are the denominator and the argument to trig functions. In this case, I have x squared. I can see that I have an x on the outside, but the problem with replacing x squared with u is that it will give me a sine of u over a cosine of u, but maybe that will be enough. Let's see if that will work. If I do that, then I would get the following. I would have u equal to x squared. Du would be 2x, and we abuse the notation by swinging the differential dx around so we can solve for du. I don't have the 2, so I can divide by the 2, and that would give me that x dx is equal to du divided by 2. You can also instead always solve for dx and then use the substitution for just dx. That would leave the x in there and it would cancel with this x, leaving you with the same result. In this case now, I'm going to rewrite the problem. The x dx part here gets replaced with a du and a factor of 1/2. I can split those apart and put the factor of 1/2 as a constant out front. Then I replace x squared with u and write sine of u over cosine of u. Now I need to look at it and go, well, what can I do with that? There are a couple of different ways you could go. In this case, I need to know what I can do. This is another u substitution. Since I've already used u here, I need another letter. Typically when this happens, we switch to what's called omega. So now I'm going to switch to omega. I need another u substitution, and yes, omega does look like a lowercase curvy w. In this case, which of these would make the better choice for our new u, which is omega? Typically, when it's a choice between the numerator and denominator, it's usually the denominator. The reason being that we're trying to develop a 1 over u du so we can use the natural log of u. This would lead to omega being the cosine of u. Now I need to take the derivative of omega, but not with respect to x, with respect to u, since that's what the previous differential was. When I take the derivative of cosine with respect to u, I get negative sine of u. Now I can abuse the notation and swing the differential du around to the other side. That leaves d omega is equal to negative sine of u du. I don't have the negative, but I do have sine of u du in the integral. That means that the sine of u du must be equal to negative d omega. I can replace the sine of u du with negative d omega. The 1/2 stays as a factor at the front, and I replace the part of the differential with d omega and a negative. The negative is a constant -1, so it too can join the 1/2 on the outside. Now I need to substitute cosine of u in place of omega, or rather vice versa. We'll replace cosine of u with omega. This leads to 1 over omega d omega. What does that give us? Okay, if we continue along this path, I need to integrate this. However, 1 over omega d omega is just the antiderivative for natural log. This gives me -1/2 the natural log of the absolute value of omega plus a constant. Now we have to do a fair amount of back substitution. First, I back substitute out of omega to get back to u. This leads me to -1/2 the natural log of the absolute value of the cosine of u plus a constant. Then I need to back substitute out of u and get back to x. U was x squared. That leads to -1/2 the natural log of the absolute value of the cosine of x squared plus a constant. And that would be the final result. It's a pretty tricky problem with 2u substitutions, and though it initially looked as though it didn't involve exponentials and logarithms, in fact it did. It did lead to 1 over omega d omega, which is the natural log of the absolute value of omega. Let's take a look at another example. In example 10, we have another tricky indefinite integral to find. Again, we've got multiple places to look for a good u. We have natural log, so its argument is a good place for u, though with the complexity of this integrand, I don't think that will be where we find it. Denominators are also good places to find u, but this denominator looks too simple to me. On the other hand, let's take a look under the radical. The radicand itself is another good place to find u. So far we have 3 good places, but there's actually a fourth, and it's the fourth one that we actually want. The fourth good place to find u is that something is being raised to the second power. When you have power functions, then a good place to find u would be the thing being raised to the constant power. In this case, natural log. Why did I know to go for natural log? Yes, there's a natural log on the outside, but if I let natural log be u, then this also becomes u on the outside. I thought of natural log because the x in the denominator can be thought of as a 1 over x. In other words, I could instead think of the problem like this: 1 over x times natural log of x times the square root of 1 minus natural log of x, quantity squared, dx. In this way, I can see that if natural log of x is u, then this becomes u, and this will be a part of du along with the differential dx. Let's make that substitution now. We are going to let u be equal to natural log of x so that du can be 1 over x times the differential dx after we abuse the notation. Now, in the next step, let's ring the parts that are being substituted out. The 1 over x dx is going to be substituted with du. We're also going to be replacing the natural log of u here under the radical in the power and here on the outside with u. Let's do those substitutions and rewrite our integral. This will result in the indefinite integral with 1 over x dx replaced by du, the natural log on the outside replaced by the monomial factor u, and the natural log of x under the radical replaced by 1 minus u squared. Now that I'm looking at this problem, it becomes a totally different indefinite integral. I'm starting all over. I'm wondering, can I do a u substitution? And the answer is, yeah, I think I can. Where's a good place to find u? I don't have a denominator, and I don't have an argument to a trig function or natural log, but I do have a radical, which makes the underside of the radical a good place to find u. In this case, I'm going to rewrite it now, and I'm going to choose instead for omega, my second u substitution, to be 1 minus u squared. Now I need to take the derivative of omega, but with respect to u, since that was the previous differential. This will give me the derivative of 1 being 0, negative 2u. Now I can abuse the notation and swing the differential du around to the other side so I can solve for d omega. D omega becomes negative 2u du. Now I can substitute. However, notice I don't have a negative 2u du. This time, just for fun, let's solve only for du. If I solve for just du, this would lead to du equal to d omega divided by negative 2u. Rewriting the integrand then, to do the substitutions, I would have the integral of u square root of, I'm replacing 1 minus u squared with omega underneath the square root. Let me shorten that up a little bit. And then on the outside, I'm going to replace the differential du with d omega divided by negative 2u. Again, you can solve these either way. I have no preference. Use the way that makes the most sense to you and the one in which you make the fewest careless mistakes. That's my advice. Notice that you have cancellation of the monomial factors u, and the negative 2 that's in the denominator becomes a constant factor that can come outside. This will give us negative 1/2 the integral of the square root of omega with respect to omega. Now you can think of the square root of omega as omega to the 1/2 power, which will allow me to now rewrite it in power form as omega to the 1/2 d omega. Then I can apply the power rule for integrals, which would lead to negative 1/2 times omega to the add 1 to 1/2 gives me 3/2. Dividing by 3/2 is the same as multiplying by 2/3. Don't forget the constant, which gives us the family of antiderivative functions. In my next step, notice that the 2's will cancel and I get left with negative 1/3. And this will be multiplied by omega to the 3/2 power plus c. I need to now back substitute all the way back to x, but first I go from omega to u by replacing omega with 1 minus u squared. This leads to negative 1/3 times the quantity 1 minus u squared raised to the 3/2 power plus a constant. Now I need to go from u back to x. My original substitution is that u is the natural log of x. Scrolling down, this then leads to negative 1/3 times 1 minus, in parentheses, the natural log of x quantity squared to the 3/2 plus a constant. It is tempting, because the 1/2 power represents a square root, to want to take the square root of the 1 and the u squared, or the natural log of x squared. However, you cannot do that because of the subtraction. That can only happen when you have strictly factors and divisors, things multiplied and divided. If you have addition and subtraction, hands off. That was the last example for this video, and that completes the video on integrals involving exponential and logarithmic functions. In the next video, we'll be taking a look at integrals involving inverse trig functions.